So periodically, we check the periodic table and look for patterns. That's what the subject of this podcast is all about. Looking for patterns in the periodic table. Thus the name periodic trends. So we talked about the meaning of all four of these terms in class recently. And so just to review, I wanted to put some of those things up here. So I've clarified the definitions that we talked about in class over the last few days, and just take a moment, maybe pause the podcast and try to digest these so that they make more sense to you. One note that is worth mentioning is that if you look at the trends, and we'll go through that in a minute, the only one that sticks out as very different in large part is atomic radius versus ionization energy. The reason, although we won't get into the details of this class, is these terms, ionization energy and electron affinity, are actually a mathematically combined set of numerical values that then give rise to the electronegativity. You don't need to know how that calculation occurs, but that is part of the reason why these three all tend to go in the same direction. So in summary, if you look at the periodic table, there's regions of the periodic table where the atomic radius is lowest. Along that same line that is where the ionization energy, the electronegativity, and the electron affinity are at their max. And then conversely, where other regions of the periodic table, the lower left corner, where the reverse trend exists. Why that is, why each of those properties are the way that they are, center on the common theme of where is the pull by the nucleus on the electrons the greatest, and where is the pull or attraction for the outer electrons on the part of the nucleus the least. And so if you look at the regions of the periodic table, there are definite extremes to one another. Understanding the trends and the reason behind the trends is a little bit easier to do with group trends as opposed to period trends, and that's what I'm going to talk about now. If we look at the Bohr diagrams, which you're familiar with for lithium, sodium, and potassium, which are in the first group of the periodic table, you know that what they have in common is a similar number of valence electrons, 1. They have increasing number of energy levels, and also in the nucleus they have an increasing number of protons. So the impact of these properties depends on the changes that are going on in the group. Number 1, more protons in the nucleus. Number 2, more energy levels. And because there are more energy levels, the outer valence electron, in the case of lithium, is shielded from the nucleus in the center by 2 electrons. In the case of sodium, the outer electron is shielded from the nucleus by a total of 2 plus 8. That's 10 electrons. And then finally, in the case of potassium, the outer electron, potassium, shown over there, is shielded from the nuclear charge of 19 protons by a total of 18 electrons. And so it is this shielding that actually has the largest impact on the properties in a group. Looking at 2 groups simultaneously, we can again see the similarities in the number of valence electrons, but also a gradual increase in the nuclear charge while a corresponding increase in the number of energy levels that shield the nucleus. In other words, these are called the inner energy levels, or sometimes called the core electrons. When you write the shorthand electron configuration and you put in brackets the noble gas, here the core electrons, number 18, neon 10, helium 12. These are the core electrons that are shielding that nuclear charge. Likewise in the alkali metals, argon, neon, and helium. 2, 10, and then 18 electrons in the core, shielding that positive charge of the nucleus. So when you look at that, you see in general that, number one, you have the same number of valence electrons. 2, you have an increasing number of energy levels and an increasing number of protons. But what you have is a greater amount of shielding by the core electrons of the nucleus. So in essence, you have a lesser pool at the bottom of the periodic table because this outer electron is so far away and shielded by the nuclear charge that, in essence, the pull is less on the outer electrons in bromine and potassium than it is fluorine and lithium. Now, the other question down below is the obvious question of metals lose electrons, whereas nonmetals gain electrons. Hopefully, you've been able to answer that question just by thinking about it. Metals, I guess, could gain 7 electrons and have their S and P orbitals filled, and likewise the nonmetals could lose 7 of the halogens. But does that make sense? Think about the energy required to do that. Here's another look of the decrease in the hold or attraction for the outer electrons by the increase in shielding. Hopefully this visual will give you a point of comparison. However, if we look across a row of the periodic table, in this case the second period, just picking several elements, lithium, carbon, and fluorine, we have a difference across a row as opposed to going down a group. So in this period, we have the same number of core electrons. In this case, there are 2 core electrons in each case. We have an increase in the number of electrons in the second energy level, but again, the electrons are all being added to the same energy level. We also have an increase in nuclear charge. So, effectively, the pull on this outer electron, 3 same core on 1 electron versus 6 versus 9, it is as if the magnet, meaning the protons in the nucleus, is more powerful. So it has a greater ability to pull on these outer electrons. So what happens to the effective nuclear charge going across the period? It increases. So in summary, if you look at the next slide, you see that the greatest pull is at the top right and the weakest pull on the electrons in the lower left. The impact is that when we go to look at the ionization energy, it's going to be hard to remove an electron, ionization energy, at this end of the periodic table, but it's going to be easy to remove an electron at this end. That's why metals want to lose electrons. It's very easy to remove an electron from an alkali metal, but very challenging to try to remove an electron from a halogen. So it takes a lot of energy. So in terms of electron affinity, again, that ability to attract an electron and become more stable, fluorine and the other halogens have a very high electron affinity. And that's why nonmetals gain electrons. So we have metals losing electrons. Why? They have low ionization energy. Nonmetals gaining electrons, they have high ionization energy. But what about noble gases? Well, do they really have an affinity for electrons at all if their outer energy level is filled? In chapter 7 in 8 and 9, we're going to get into bonding, and that's where electronegativity really comes into play. So far, we've differentiated ionic and covalent compounds by the distinction between metals and nonmetals. And we say that ionic compounds are those compounds where an electron is transferred from a metal that wants to give up an electron to a nonmetal that wants to gain an electron. And we said that those electrons are transferred as opposed to shared. And when we have two nonmetals, both of those nonmetals really want to achieve the same thing, an octet. But instead of them one giving up an electron and the other one gaining it, what happens is there's a mutual sharing or a somewhat unequal sharing of electrons. And that's the subject of Chapter 8. So we'll pause on a further discussion of how we use electronegativity until we get into that next chapter. So a few notes about the irregularities of ionization energy, removing more than one electron from an atom, which is called successive ionization energy, comparing the size of an ion to an atom. So that's what I want to talk about next. So the irregularities in the ionization energy. Now, if you think about the trend going from beryllium to boron, you would think that beryllium would have, since the periodic trend is increases going across the periodic table, you would think that boron would have a higher ionization energy than beryllium, but the reverse is the case. And so why is that? It has to do, and it's helpful, if you write the electron configuration of boron and beryllium. And when you do that, and if you remember that both filled and half-filled sublevels are particularly stable, and if you think about the fact that these 2s electrons are shielding this electron, you can see how it might be easier to remove one electron from boron than a filled sublevel, i.e. stable, for beryllium. So that's why if you look at your graph of ionization energies, highlighted in yellow is the beryllium and boron ionization energy. So instead of that general increase in ionization energy as you go across the periodic table, there's a slight dip down. It's almost as if beryllium is a little higher and boron is a little lower than you would expect. And a similar situation arises if you compare the ionization energy of nitrogen and oxygen. Highlighted in green, you can see that the nitrogen, which now has one electron in each of the 2p orbitals, is half filled, a little bit more stable, a little bit more energy to remove one electron from the nitrogen, as opposed to oxygen, which actually has 4 electrons in the 2p orbital, so it's one more than half filled, so there's a slight dip. Now if you go to the next period, which starts with sodium and goes across, you see the same dip down between magnesium and aluminum, and then phosphorus and sulfur. So if you take a given atom, in this case let's just take magnesium, and you remove one electron, takes a certain amount of energy. You can imagine that removing a second electron and then a third and a fourth, the amount of energy required is going to gradually increase, and that is indeed the case. However, if you look at the values, and these are found in your textbook, they're called successive ionization energies. If you look at the ionization energies, where you see a big change in the amount of energy to remove an electron comes after you remove 2 electrons from magnesium. To remove the third requires a phenomenally greater amount of energy. Can you explain why? If you wrote the electron configuration of magnesium, you would see that magnesium has 2 valence electrons. So removing the third electron, you're going to be cutting into a filled energy level, the filled valence shell, or a filled inner shell, and that is the reason why you can, and if you had an unknown atom, if you could look at where there's a big jump, you could predict, oh, this substance must have only 1 valence electrons or 2 valence electrons, whatever, based on where you see the biggest jump in the ionization energies. Now I'm going to stop the podcast here, but I want to call attention to these multiple choice questions that are found at the end of this Smartboard notes. So you might consider looking at all of these questions. The answers are found at the end of the Smartboard notes. And if you want, you could use your ebook. The OWL problems are similar to the ones in your textbook. But if you'd like to use the ebook to explore some additional videos, that might be a good idea as well. So for now, check out these multiple choice questions on the Smartboard notes, which are found on Edline. Hope the video has helped you.